Okay, let's configure the next part of our lab. Let's go for the next action item, which is 3.a, compare routing concepts of EIGRP and OSPF. So let's jump into the theory, and there is a lot of ground to cover. I will try to be brief. Let's compare EIGRP with OSPF. EIGRP stands for Enhanced Interior Gateway Routing Protocol. There are several versions of EIGRP out there. For instance, when using named EIGRP, we could be able to run IPv6 with VRFs. OSPF stands for Open Shortest Path First, and there are several versions. Version 3 supports IPv6. Now, these are the topics that we are going to cover. Let's go for the first one. Regarding protocol type, EIGRP is considered to be an advanced distance vector protocol. It is no longer considered to be a hybrid protocol. It was previously defined as hybrid, but Cisco has dropped this definition over time. OSPF is link state. Now, regarding routers, EIGRP routers only have a partial view of the network because they route by rumor. That means that the only information each EIGRP router has comes from its neighbors, whereas OSPF routers have a complete view of an area. When it comes to standard, defining whether these protocols are standard or not, EIGRP was born proprietary. However, later on, around 2013 or 2014, and Cisco released an RFC for EIGRP, so any vendor can go read the standard and release its own version of EIGRP. However, nobody has done that, so EIGRP is still a Cisco thing. OSPF is and has always been a standard. Now let's examine how EIGRP actually works as an advanced distance vector protocol. Let's imagine that we have this new network 10.1.1.0/24 that is getting connected to router A. What will happen then? As soon as this network comes up, router A will send an update to all of its neighbors. Remember that EIGRP works with router by rumor, so green router A will send an update to blue router X and an update to blue router Y. Now, when receiving this update, blue router X will update all of its neighbors. For instance, it will send an update to yellow router V, and it will try to send an update back to green router A. So in this case, a rule kicks in that is known as a split horizon. A split horizon rule establishes that if a router receives an update for a certain prefix on a certain interface, that router must not send this update back for this prefix on this interface. So using this rule, this update will be blocked. So thanks to split horizon, we are going to avoid having update loops. The same happens with the blue router Y. As soon as it receives the update from the green router A, it will send an update to all of its neighbors, including yellow router V, but it will try to send this update back to green router A. In this case, the split horizon will not permit that this update gets sent, and this will happen at every single router. For instance, when yellow router V receives these updates from the blue routers, it is going to try to send an update back, but a split horizon is going to deny permission to do so. So split horizon is our friend. Notice that with some certain network design, a split horizon can become an issue. So for instance, think of this hub and a spoke topology. When we have only one interface here that is going to receive updates from the spokes. Examples of these technologies are, for instance, DMVPN. So in these cases, a split horizon becomes an issue because the update coming from this router arrives to this hub, but if we allow a split horizon to operate on this interface, this hub will not be able to transmit these same updates to the other routers, to the other spoke routers, because split horizon will not provide permission to do so. So in certain network designs for EIGRP, we have to disable a split horizon. Now, continuing with our example, what do these routers actually going to perform when receiving these updates? So, for instance, when blue router X receives this update from the green router A, it's going to do mainly two calculations. It's going to calculate first the reported distance, also known as advertised distance, and this is the metric calculated from the green router to the destination prefix. So in the router X is going to calculate this from the standpoint of green router A. So it will also going to calculate the metric from itself to the destination prefix. It is going to look after the best metric, and it is going to call that the feasible distance. Something similar happens when the update arrives from the green router A into blue router Y. It is first going to calculate the metric from the green router A standpoint, and it is going to call that the advertised distance or reported distance. It is also going to figure out what is the best metric from itself to the destination prefix, and it is going to call that the feasible distance. Now, at router yellow, something similar will happen. When receiving the update from blue router X, router in yellow is going to calculate the metric from the standpoint of router X to this prefix, and it is going to call that the advertised distance or reported distance, the same from the standpoint of the router Y, and it is going to call that the advertised distance or reported distance, and it will figure out what is the best metric to reach this prefix from itself. It will call that the feasible distance. All this information is going to be stored in the EIGRP topology table. So router B will have its EIGRP topology table with router Y reported distance, router X reported distance, and the feasible distance. The same applies for router Y. It will store this information in its EIGRP topology table with on router A reported distance and feasible distance. And the same will apply for router X, and so on. So let's compare that operation mode with link state protocols such as OSPF. In this case, with link state protocols, each router is going to generate LSAs. For instance, each router must generate an LSA A of type 1, which is the router LSA. So these LSAs will contain actual information about how these routers are connected to each other. Eventually, these LSAs land into a linked state database. When this database is complete and it is synchronized, then each router will create into memory a tree view of the network. These routers will have enough information to see how the whole network is connected, and they will place themselves as the root of the network in this tree, and they will calculate cost to each destination within the network using the GSTRA algorithm. So that is the main difference of how linked state protocols work compared to an advanced distance vector protocol such as EIGRP. Now let's see how the path selection happens. With EIGRP, we are going to use a formula. We have two formulas, mainly the 5K formula, which is the classic metric formula, and the 6K formula, known also as the wide metrics formula. Using these formulas, we are going to choose the best metric to reach a destination, which is the lowest metric, and we are going to call that the feasible distance, which is the lowest metric to reach a destination. And then the router that will let us reach that destination, the next hop, is going to be the successors for EIGRP. For OSPF, we are going to calculate the summation of cost from the current router to each destination. For each destination, the path that has the lower summation of cost becomes the best metric. So we are going to calculate this total cost, and the router that allows us to reach each destination is going to be called the next hop. Now let's see how EIGRP operates in detail. For instance, let's say that we have this path that is the best path to reach this destination, and for that path we have calculated that the metric, which is the best metric or the lowest metric, is going to be called the feasible distance, happens to be 1500. Now the router that allows the yellow router to reach this destination for the best path is router X. So we are going to call router X the successor. In all of this in EIGRP terminology. Now EIGRP also calculates other alternate paths. So in this case, there is something that is known as the feasible condition. The feasible condition happens when a neighbor router reported distance happens to be lower than the feasible distance. So let's analyze router Y here. The reported distance calculated for router Y happens to be, in this example, 1250. In this case, 1250 happens to be lower than the feasible distance, which is the best metric to reach this destination. So this is lower than 1500. So this complies, this abides by the feasible condition. In this case, we can reach the conclusion that the feasible successor to reach this destination is router Y. So this is actually an alternate path to reach the same destination. So compare that with OSPF. OSPF simply synchronizes a linked state database, and then it will going to create a tree in memory where it places itself at the root of this tree, and then it will start calculating the cost to reach each destination. So for instance, in this example, the summation of cost for this path is 8, and for this other path the summation of cost is 16. In this case, this path wins and this metric is placed into the routing table because this is the best, given this is the lower path cost to reach this destination. Now, let's talk a bit about load balancing. In this case, when it comes to equal load balancing, both EIGRP and OSPF support equal load balancing. What equal load balancing means? This happens when you have a router and you have, for instance, two links, and these two links have the same metric to reach a destination. So, for instance, link A has a metric of 10 and link B has a metric of 10. The same exact metric. Now, we want to load balance, we want to avoid having one link idle, so we are going to set max path, the max path variable, at least to 2. It can be 4, it can be 8. So if we set max path to 2 and we had two links with the same metric, we can start load balancing, sending some packets destined to this destination using this link and some other packets using the other link. So this is equal load balancing. Unequal load balancing involves doing the same but for links that have different metrics. With EIGRP calculations, it is really difficult to have two links with the same metric. So that is why Cisco designed EIGRP to support unequal load balancing. In this case, we are going to validate this. We are going to set up a variance value. So for instance, let's say variance is equals to 3. And then we are going to divide this non-best metric by the best metric, and we are going to obtain a number. As long as this number is lower than variance, we are going to perform unequal load balancing. So for instance, in this example, the best metric is 10 and the not best metric is 20. So we are going to divide 20 by 10. So the value is 2. If we set up the variance value to 3, then this is true, and then we are going to be able to use this other link to load balance traffic. This is not supported by OSPF. Now let's see that in an example. For instance, we have set max paths to 2, we have set variance to 3, and we have this metric. This is the best metric to reach this destination, 1500, and this is the metric that didn't win the contest. So, and this metric is 3000. So let's evaluate 3000 divided by 1500. So we obtain 2. 2 is less than the variance. Variance is set to 3. So this complies with the formula. So we are going to use these two links to load balance traffic. This only applies to EIGRP. Now for OSPF, remember that we are going to synchronize our link state database. We are going to then create a tree on memory, and then we are going to place ourselves as the root of this tree, and then we are going to run the Dijkstra algorithm, and then we are going to calculate the summation of cost for all the paths. So in this case, the summation of cost is 3. In this case, the summation of cost is 3. So we have two paths with the same cost. In this case, if we set up, for instance, max paths and we set it to 2, we will be able to load balance between these two links. Now let's see what happens if a failure occurs in the network. So in this case, yellow router loses reachability for the successor router X. So in this case, for EIGRP, a question arises. Do we have a feasible successor for this destination? If the answer is yes, then the feasible successor becomes the successor for that route. A switchover happens almost instantly, and no time is taken for this convergence process. However, if there are no feasible successors for this destination, then the EIGRP dual process kicks in. Dual becomes active, and this prefix is tagged as active in the EIGRP topology table. This means that this router that has lost a successor for a certain prefix will start sending dual queries. It will send a dual query for every single neighbor that this device has. In this case, the yellow router only has one neighbor, so it is going to send a dual query to router Y. In this case, router Y will have to check its rev to see if it knows a destination for this prefix, if it knows a path for this prefix. If there is no information regarding this path, it will have to forward this dual query to its upstream neighbors. So it will have to do so by every single upstream neighbor that it has. So in this sense, you can start to see that dual queries are going to flood your network looking for an answer. When this dual query reaches the green router, let's imagine that this green router actually knows a path to reach this destination, then this green router has to answer with a dual reply. Router Y has to forward this dual reply to the original router that generated the dual query. So now at this point, the yellow router has an appropriate route to reach this prefix, and it no longer tags it as active, it becomes passive, and the convergence finishes. In this case, we have imagined that router Y didn't have a path for this prefix, but we know that router Y will have a path for this prefix, so this was only an imaginary scenario. However, let's see another scenario where an event happens here, and then this yellow router has more upstream neighbors. In this case, the yellow router has 3 neighbors, so it's going to send 3 dual queries. In this case, let's say that this dual query reaches router C. Router C happens to be the edge of the autonomous system, so there is nothing beyond router Z. So probably this has other networks such as the internet or other type of networks. So this is what we know as a query boundary. So when dual query reaches a router that is actually a query boundary, this router will answer with a dual reply because it cannot forward this query anymore to upstream EIGRP routers because it doesn't have any other upstream EIGRP neighbor routers anymore. There is nothing anymore for the EIGRP domain. That is why dual reply is sent. So the process for this interface is done, finishes, And let's see what happens with this router. Let's say router M. This router is going to forward this query upstream. Each router has to check if this prefix still exists in its topology tables. So if it doesn't exist, it has to be forwarded upstream until this query reaches this router, let's say router N, that happens to be tagged or configured as an STUB router. These routers marked as a STUB are also query boundaries. So this router here will have to reply with a dual reply stating that a query boundary was found. So finally the response is sent back to the yellow router. And let's see what happens with the other query. This router sent it upstream and this router sent it upstream, but in this case this interface is performing a summarization. In this case, this summarization is including this prefix here. However, this router, let's say P, says that it doesn't have anything related to this prefix. So as this is a summarization interface, the process ends there because summarizations are also query boundaries. So our response is sent back and is forwarded back to the originator. In this case, the yellow router notices that it has 3 neighbors, it has sent 3 dual queries, and it has received 3 dual replies. It reaches the conclusion that this prefix no longer is reachable and it will delete it from the topology table. Now, in catastrophic events, there are cases when routers send dual queries, but after some times the replies never come back. If for a certain prefix queries have been sent and replies are not coming back, this prefix is said to become stuck inactive. We don't want stuck inactive. This means that there is something wrong with our network. That means that we have to review our network topology, redesign it, because stuck inactive routes are red flags for EIGRP. We don't want to see stuck inactive routes. Okay, let's see how the OSPF path operation works. If something happens in the network, the routers will have to refresh their LSAs. These LSAs that has been refreshed eventually reach all the routers. The link state database gets synchronized, so routers then build a root styled network, and then they place themselves as the root of this tree network. They place themselves as the root, and they will run the Dijkstra algorithm. So with this process, they will reach probably a different path to reach all the destinations that were lost due to this failure. Notice the difference between using dual and using link state processes. Now let's talk about the metric. Now let's see how the metric is calculated for EIGRP. It's a composite based metric because we are going to take into account minimum bandwidth, load, summation of delay, reliability, MTU, and a reserved value. Most of the times these multipliers that are known as K values are going to be set to 0. So we usually have key1 equals key3 equals to 1. So we are going to take into account only minimum bandwidth and the summation of the delay for EIGRP. For OSPF, we are going to do some summation of costs. Notice that the cost is calculated with this formula. This formula no longer is or represents meaningful cost for interfaces that are greater than fast Ethernet. So for instance, 1 gigabit per second interfaces have a cost of 1, 10 gigabit interfaces have a cost of 1, and so on. So you might change this value that is known as reference bandwidth to a larger value. If you do so, you have to change that in all your routers. Now, how do you influence these metrics calculation? So for instance, let's say that you have one router and you have 2 links, and this link happens to have the best metric, but you want to use these links instead of this one. You can change for EIGRP the bandwidth, which is not recommended, or you can change the delay. In the case of OSPF, you can change the cost. Now, regarding the formula for the metric for EIGRP, there are 2 formulas. The 5K formula, that is known as the classic metric formula, that will create a 32-bit number, or you can use the more recent formula, which is a 6K base formula known as the white metric formula, that will generate a 64-bit number. Now, when it comes to OSPF calculating the metric, it is going to use LSAs that are going to be translated into a 3, and then this 3 will actually have costs. So for instance, the path from this, the cost for this path will be 3, and the cost for this other path will be 3. Notice that these LSAs are created by all OSPF routers, and they have to be refreshed every 30 minutes. Once these LSAs land into the link state database, they must exist there for no longer than 1 hour. So if you take a look at your link state database and you see LSA that has more than 30 minutes, something is wrong with your network. Some event happened. Now let's see, for instance, the link state database. In this case, we have these LSAs type 1. These are the router LSAs. This means that our OSPF domain has 5 routers. This is the age. This usually go up to 30 minutes and then it gets reset. However, if you see something that is going larger than this number, this means that something went wrong with one router. And these are the LSAs type 2, which are corresponds to networks where more than 2 routers are connected to. So for instance, these correspond to broadcast networks. Now let's go for EIGRP formulas to calculate the metric. This is the classic. You should actually memorize this for the exam. However, in real life scenarios, this becomes 0 because these K4 and K5 are 0, K2 is 0, So you end up with this part of the formula, this part of the formula, and this number. So in real life scenarios, this is the way to calculate the classic bandwidth, classic metric. You need the minimum bandwidth, the total delay, and this is how to calculate it. Remember that these calculations are done using integers. No floating points are used here. Now, we have an issue with old iOSs. When this X router sends an update to this B router, for old iOS, the delay and bandwidth are not sent as the actual value. They are sent in a mode that is known as scaled. So when this X router calculated its metric, it used these formulas and it stored these values, and it is actually using these values for the update. So this involves a little hassle for router V, because upon reception of these values, it has to unscale these values in order to gather the actual bandwidth and summation of delay, and then update these values and then calculate this formula again to reach this conclusion. So router V will use these formulas, which is actually algebra coming from these two formulas. We just have to figure out how to calculate the minimum bandwidth at total delay. So if you don't want to use algebra, this is the formulas. These formulas are known as the EIGRP backward compatibility formulas. So this only happens if you're using old iOS, for instance, 12, iOS 12.2, for instance. But if you're using a recent iOS, for instance, iOS 15 or iOS XE, you are going to see this. These are when a router sends an update to another neighbor, the actual delay and bandwidth gets sent. So in this case, the delay is sent in picoseconds, and the bandwidth is sent in kilobits per second. The same formula applies here. So in this case, with more recent iOSs, you don't have to unscale values. So remember that this is the actual formula for the exam. Now, there is a more recent formula, which is known as the wide metric formula, 6 case values in this case, and we are going to create a 64-bit metric. So remember that we're usually going to end up using this term and this term. The others will go to 0. Now, this is an example of a wide metric formula. This is the actual formula that you will need to learn for the exam if you happen to be calculating a wide metric. Now, something interesting happens with wide metrics. Since wide metrics are 64 bits and the router information base is 32 bits, scaling has to be done. So in this case, we're going to use a Riva scale. So we're going to use the 64-bit metric, and we're going to divide that by the Riva scale to generate the actual Riva metric. Now, let's talk finally about STUB networks. If you have a really large network, you will notice that some parts of your network have really high-end routers and high-capacity links. So you might want to have all your transit within your network using these devices and these links. You want to move traffic across your network most of the times using these high-end routers and high-capacity links. So, and you want to avoid moving traffic across low bandwidth capacity networks or remote branch networks. So in this case, you can divide your network into a part where you want to define this as a transit network, and you want to define parts of your network that will be actually a stub, that where you don't want to this part of your networks to become transit networks, because that part of your network has low bandwidth capacity, or because this part of your network is a remote branch network. So you want to set up this as your stub network, this as an stub network for stub areas. Now let's put an example. For instance, let's say that you have this setup. You have a corporate network and a data center, and you have these high capacity links, these high capacity devices here, and you are using them to actually, for instance, transfer database, replication, application, and so on. And then you need to set up a new network, a temporal convention network. So because this company has to show the products, and then you have to set up this temporal convention network. This temporal convention network is only to be able to work for 2 weeks. It is temporal, and it still needs access to your corporate offices, and it needs access to your data center offices. So in this case, you really don't want this network to become a transit network between these two locations. You don't want that. You want to have this or use these high capacity links and high capacity devices to always be used for transit. So one way of achieving this will be configuring this network as an STUB network. With this, you will guarantee that under no circumstances this network will become a transit network. Let's put another example here. For instance, you have a branch office that is connected to your corporate network, and in this case makes a lot of sense to define this as an STUB network and define these two parts of your network as your transit. So when it comes to EIGRP, you have two types of networks: normal area or areas, and stub areas. The part of your network that is the normal area are transit networks where dual queries are forwarded until a query boundary is met, whereas an stub area is a non-transit network that are connected at least through a router known as the STUB router. STUB routers are query boundaries. So for instance, you may have this EIGRP design where this is you have a branch network here, but this branch network is connecting to the data center and your corporate network, but you really don't want this branch network to ever become a transit network between these two other networks. In this case, you will define this as an STUB EIGRP STUB area. In order to do so, you will configure here in this router the STUB flag, in this router the STUB flag, and these routers will actually become a dual query boundary. So if some router here is starting to send queries, the queries will stop here. Queries will not reach this part of the network. Now compare that with OSPF. With OSPF we have normal areas, STUB areas, totally stubby areas, not so stubby areas, and totally stubby areas. Let's see an example of normal areas. In this case, we can define, for instance, this as our backbone area, and we have this other part of the network that is also providing high capacity for bandwidth, and we have also connection to the internet here and other autonomous system, remote branches. So you can set up this as a normal area number 1. So that is one way of doing it. This normal area has high capacity, so there is no reason to see it as an STUB. But what happens if we have a low capacity branch that is even geographically remotely connected to your corporate server? So in this case, you can set up this as your normal backbone, and then this could be an STUB area for OSPF. Notice that you will still be receiving these intra-area LSAs, for instance LSAs number 3. And this network, notice that this network is completely STUB. You are not connecting anything here. You don't have autonomous system border routers here. You don't have that. We can go even further and make this STUB, but we are going to disallow LSAs number 3, and we are not only going to inject here a default route into my area, and then we are going to call that a totally STUB area. Let's break the rules for STUB areas and permit this branch to have an autonomous system border router. So we are breaking the rule here for STUB areas, and then if we break the rule, this is going to be called a not so stubby area. We are still going to allow LSAs number 3 to enter our STUB area. And let's go even further and have now our not so stubby area filter LSAs number 3 from entering, and then injecting only a default route for reaching the OSPF domain. So that will be called a totally stubby, not so stubby area. Now that will be all for the comparison. However, there are other differences that we didn't go into detail between EIGRP and OSPF. For instance, the protocol number, EIGRP uses 88, OSPF uses 89. The multicast IP address that these protocols use in order to work, EIGRP uses 10 and OSPF uses 5 and 6. Both are classless routing protocols. However, EIGRP can become classful if you use these commands. The timers, EIGRP uses a 3 multiplier for the timers, for Ethernet 5 seconds and 50 seconds, 60 seconds and 180 seconds for the hello and dead timers, whereas OSPF uses a 4 multiplier for the timers. The hello timer is 10 and 40, or 30 and 120. For OSPF, these timers must match in order to create neighbors. For EIGRP, these timers must really not match in order to create neighborships. OSPF will create periodic updates with a refresh for the LSAs every 30 minutes, where EIGRP does not send periodic updates. EIGRP does not have neighbor states, whereas OSPF has neighbor states down in it. Attempt to wait X start, X exchange, loading, and full. When configuring EIGRP, these numbers actually matters. This is the autonomous system number used to as a condition to create a neighborship. However, when configuring OSPF, this number is only a process ID. It is actually it actually has only local significance. Now, the conditions to become neighbors for EIGRP: subnet must match, autonomous system must match, key values must match, and the authentication must pass. For OSPF, the subnet must match only for OSPF version 2, area ID must match, STUB, the STUB flag must match, the hello and the timer must match, MTU must match, the router ID must be unique, authentication must pass for OSPF version 2. When it comes to summarization, EIGRP only works on interface level, and for OSPF, summarization is performed at area border routers. These are the packets for EIGRP: hello, request, update, acknowledge, dual query, dual reply, stuck inactive, dual query, stop inactive, dual reply. Whereas in OSPF, we only have hello, database definition, link state request, link state update, link state acknowledge. This is the summary for the comparison between OSPF and EIGRP. That's it.